Hi, everyone. Thank you for joining us. Good afternoon and warm welcome. My name is Samrat Priyadarshi, and I'm joined by my colleague Anmol. And today we are going to talk about a very interesting topic, an emerging topic called quantum computing, and how we can use the cloud-native stacks and tools to run your quantum simulations. So I believe the audience might be cloud native focused. So the agenda is to, go through the basics of quantum computing and how we can use the quantum simulations on some of the cloud native tool stacks. So moving on, so we both work for Google and we heavily invest in emerging technologies, and we love to share it with the community, and that's why we are here in this conference. So just a quick disclaimer. So whatever we share here, the views and contents, it's just us, our experiments, and it doesn't relate with the organization that we are associated with. So this is a very action-packed agenda that we have, and we'll try to finish it in the time that we have. So first of all, we'll look at the basics. Which is, what are some of the principles that quantum computing leverages from the quantum mechanics, and what actually makes the quantum computing work. And then we will dive a little bit deeper into why you should care as a cloud-native audience about quantum computing, and how we can run those simulations on, the cloud-native stacks, etc. What are the challenges and all those things. Then we'll dive a little bit deeper into the building blocks, which means the gates, the visual representations that we can do for the bits, etc. And then Anmol will take over, and then we'll dive into the deeper advanced topics. And then those will be focused on some real-world applications and the demos that we have prepared. And finally, some of the key takeaways, and we'll take questions after that. So with that, let's get started. So basically, I'll compare first with the classical bits that we have, which is 0 and 1 that we have seen or we use on a day-to-day basis, this laptop or whatever, the phone, etc. Everything is 0 and 1, right? That's the classical computer that we work with day in, day out, right? But quantum computing, it leverages something called quantum bits, or qubits for short, which again is represented by 0, 1, but we have a phenomena called superposition, which means that 0 and 1 can exist at the same time, right? So that's where, all those experiments that we have read in, our colleges or schools, the double slit experiment, etc., those all demonstrate this superposition principle. So, and this is, I think, the one of the major foundations for the quantum computing that we see. And then the other two important quantum computing principles are entanglement and interference. So basically, entanglement means that one qubit is associated or synchronized with other qubits. So if I have to, if I know a value of a particular qubit, I can measure the value of the other qubit no matter where it is, no matter when I measure it, etc. Right? So that's called entanglement, and that's also a very important concept, and you'll see why in the demos that we have. And then we have interference, which basically means that we can yield some results faster. There are two types: constructive, deconstructive. So, for example, we have two waves, and if those two waves have peaks at the same time, then that peak will be higher. And if the waves have peaks and lows at the same time, then it will be negated, right? That's deconstructive interference. So basically, these three are the major quantum computing concepts that are in the any hardware that we see. And then after that, we have something called measurement. So basically, until and unless we don't measure something, it is in superposition. That particular qubit is in superposition, right? Which means it can either have 0, 1, we don't know, right? But as soon as we measure it, it is either 1 or it is either 0. And we measure all these things again in 0, 1 because, so whatever we pass to the supercomputer, that goes as a classical bit, and whatever output that comes out as a classical bit, right? So, and then we have decoherence, which means that if a qubit loses all its properties, quantum properties, then we call it decoherence. Measurement is a special type of decoherence because we are measuring it, meaning that we are bringing it back to a 0 or 1 state. Then error correction is something like, because in a particular quantum computing hardware, noise is very inevitable because of maybe something electromagnetic radiation or any kind of heat, etc. So whenever you are building some algorithm circuits, you have to factor in that noise, right? So that's the fundamentals that I wanted to quickly cover. And on the left-hand side, you can see that we have a sphere, right? So this sphere is called a Bloch sphere. And what this represents is basically, the quantum state of a particular bit, right? So that's the, representation here in a sphere. So on the top, you can see, 0. And on the bottom, you can see a 1, right? And on the right-hand side, that's the state of the qubit that it is currently in. And it's in a superposition, so that's why you're seeing that particular value. But so Bloch sphere is only useful in visualizing a single qubit. It can't measure multiple qubits, etc. And we have a way to measure that as well, which we'll see in upcoming slides. But this is just one visual representation of the qubits that we have. Moving on, right? As a cloud-native audience, why should you care about quantum computing? So basically, you all would have gone through this, the GPU phase, etc., right? And if you know about dynamic resource allocation or device plugin, etc., it was very hard for GPUs to work with cloud-native tools, right? Like Kubernetes, for example. So we started developing device plugin. We started developing the dynamic resource allocator so that we can efficiently use that particular device, right? So the same analogy applies here as well. So basically, if I need as a quantum model developer or a particular algorithm developer faster hardware, or I need that particular hardware to do on-demand simulation, how should I do that? How should I go about figuring that out? How should the platform look like? And then similar to GPUs, how can I efficiently schedule or do resource optimization in order to run my jobs, right? So these are some of the very basic problems that we will face or we are facing. And we'll try to tackle some of them in today's session. Apart from that, we also have another challenge, which is there will be multiple vendors which will build these quantum hardwares, right? Just like the GPU side of things, we have GPUs, TPUs, NPUs, etc., right? So how to efficiently use this in this cloud-native platforms, and how to short circuit that feedback loop from where I start my algorithm development to actually doing the simulation, getting the result, and then maybe again getting some feedback, and then again doing the retraining again and again, right? Because once you measure something, we have to run multiple iterations before we can certainly say that, okay, this is what the algorithm is predicting, etc. Because it's all about probabilities, and we have to make sure that we do we run our algorithms multiple times, multiple iterations. So moving on to some of the building blocks of the quantum computing, and a little bit on the circuit side of things. So here you can see some of the common representations of a quantum state. So like how can you visualize them, right? So basically there are three: state vector, Bloch sphere, which we saw earlier, and then the Kueue sphere, right? So in short, what happens is state vector is nothing but a mathematical representation, and you see that in a column or a matrix kind of things, you will have alpha, beta. Alpha basically measures the amplitude of 0. Beta measures for the amplitude of 1, right? So the higher whatever that number is. So that's the probability that we'll either get a 0 or 1, right? So that's demonstrated in the state vector. But it has some limitations as well, which is as and when the number of qubit grows, it becomes very difficult to like just represent them in the state vector, because the size grows exponentially, because it's in a matrix. So if we have a 4-qubit matrix, then it will be like 16 iterations or 16 values, something like that, right? Now the good thing is state vector helps in showing entanglement, the probabilities, the phase, etc. So that's a good thing, because we have a block sphere which only represents 1 qubit. So that's the disadvantage that it has. So that's why it's not able to show entanglement, because as I mentioned previously, entanglement is something where 2 qubits are present and 1 qubit is synchronized with the other qubit, so that we can measure the other qubit by measuring the first one, right? So we can't do that on block sphere, right? But it shows the probabilities, it shows the phase, etc. Now, the third one is called Q sphere, which overcomes some of the challenges of the block sphere, which is it helps in representing the multiple qubits, right? So it can show entanglement, which is a good thing. And just like the other two representation, it also shows the phase or angle and the probabilities. Now, one limitation here is as and when the qubits grow, like 4 or 8, whatever number of qubits you have, it becomes very difficult to plot it on a Q sphere or read them, basically. So this is how we represent the quantum state of the qubits, which you'll see in the demos as well. So this is a Q sphere. This is a 4-bit, this is showing a 4-bit quantum state. And as you can see, we have 4 zeros on the top, and we have, the 4 ones are not visible because they are, shadowed by that 1110. But what this represents is basically the lines that you see on the top, the small dot that you see. So the bigger the radius of that dot, the higher the chance of that particular state. So here you can see 16 states because this particular 4-bit qubit is in a quantum state, and you can see all of these in a Q sphere. But whatever I mentioned, so the smaller the dot that you are seeing, the blue one, the lesser the chance of that particular value. So here you can see the 4 bigger dots, which is 0, 1, 00 on the top, and 1 on the right hand side, 1 on the left hand side, and 1 on the bottom. So I can clearly say that, okay, the probability of these 4 values is higher than what I'll get, compared to the other 12 values that I have. So this shows the amplitude. And on the bottom left, you see the phase. So basically, the color is what represents phase here, which was different in block sphere. So here, blue means 0, and red means pi, right? So this is how Q sphere looks like. I just wanted to give a quick visual, just like I gave it for block sphere. And now another important thing is gates, right? So these are some of the very useful components when we design our circuits, right? Now you don't have to know about all these gates, but these are very fundamental building blocks whenever you're doing, or building your circuits. So some of them I'll cover right now, and because you'll see in the demos and some of the applications that we have built, the Hadamard gate that you see, so that basically puts a particular qubit in superposition. So that's the first thing you do whenever you start with your quantum computing journey. You put a particular qubit in a superposition, and you apply this particular gate. So these are, you can compare them with the classical bit gates, the AND, NOT, OR gates. But these are a little bit advanced because some of them work on multiple qubits, some of them work on just 1 qubit. So for example, the C0 gate on the bottom right that you're seeing, that works on a 2 bits, right? And if you recall the definition of entanglement, it needs 2 bits, right? So this is the gate which helps in entanglement between the two bits. So it has multiple things, control and target, etc. But these are the 2 very important gates that you'll play day in, day out if you're a model developer or a algorithm developer or a circuit developer. Then we have multiple other gates, poly, X, Y, Z gates. I'll not dive deeper into them, but X gate is basically, it just flips the value. So if it is 0, it'll become 1 if you apply this particular gate. If it is 1, then it becomes 0. Y-axis just flips the bit as well as the phase. Z, poly Z just flips the, just the phase. So these are some of the gates, the building blocks. There are multiple other gates as well, like CC NOT gate, the control Z that you're seeing on the top right. But yeah, I just want to cover these basics, and now I'll hand it over to Anmol to cover some of the advanced topics and some of the demos that we have prepared.
Sure. Okay. Am I audible? Now? Great. All right. Thanks, Samrat, for covering the basics. And here we are with the advanced stuff then. So basically, we need to understand that there's a lot of difference between the theory of quantum computing, because it's highly influenced by how quantum mechanics works, how quantum physics works. Depending on the branch of, let's say, science you are applying this quantum computing against, you will be requiring the context for that particular branch. Today, we are going to talk about some of the chemistry-related simulations that we will be performing through quantum computing. And hence, if you have any knowledge of chemistry, that will be helpful. Else, that's OK. I'll just explain whatever is required and necessary. Though I'm not a chemist myself, so please bear with me if I am here and there with some of my chemistry concepts. OK. So in order to realize any problem statement into real quantum world, we actually need to understand a couple of things. First, we need to understand how a qubit is formed itself, right? A qubit actually can be treated as a physical fabrication of some sort of processing system that will represent the quantum state or quantum system. And this particular quantum system could be comprised of some molecular or atomic level or microscopic level I would say, integrations and interactions that happen. Specifically, superconducting qubits are the ones which are created by things like using superconductors along with a bunch of insulators and some sort of conducting appliances. So if you have an insulator sandwiched between 2 of the superconductors, that's called the Josephson junction, the one that you see, and that's something which a lot of companies like Google and IBM are using. They actually are leveraging this transmon qubit design that we call, which is actually based on the superconducting qubits pattern. Then we actually have something called as the trapped ion qubits. Trapped ions qubits are nothing but ions are actually trapped by electromagnetic fields. There are companies investing in this area as well. So there are different ways to realize how the qubits really work. And depending on how you have realized a qubit system, the nature of errors will differ, the type of errors will differ. Some of them will be heavy on flips related to phases. Some of them will be heavy related to bit flips. So you can have a 0 jump to 1, let's say, or your superposition always end to 1 if there's a specific error which is happening, which is giving the probability of encountering 1 in the measurement. Likewise, there could be errors which could be rotating the phase. If you were to have positive, you could have got some phase rotation done. So errors are really inevitable in quantum system. You could be having errors because of any of the heat dissipation that is happening at the atomic level. You could even have some laser or some photonic interaction happening, which causes the ions to jump, or probably the atomic particles to jump from their lower energy state to some excited energy state. So that's where it's very difficult in a real world to have quantum computers work fine. Hence, we need something more important and something which focuses on scalability, reliability, as well as the stability of the overall ecosystem, because errors cannot be mitigated, they just can be detected and corrected. So that's where we come with the concept of logical qubit. On your left-hand side, you see a logical qubit. This is essentially composition of multiple physical qubits. So what we do, as we know that a specific physical qubit is not something which is self-sufficient enough because of it being prone to errors, we create a bunch of physical qubits and put them on some sort of lattice, let's say this one, which is known as the surface code lattice or repetition code lattice. In the surface code lattice, we have a specific composition. So the dots that you see in yellow are called the data qubits. These are the ones which actually are containing the data. Then you have something called as measure qubits or syndrome qubits, or you also call them as auxiliary or ancilla qubits. These are nothing but the qubits which are actually tracking if there are any changes with the phase of the data qubit or not. So these are measuring any kind of phase changes or any kind of bit flip changes. So it's more about doing parity checks. So data qubits actually retain the data. Measure qubits work on the parity checking. And then there are some leakage qubits, which are nothing but if at all your system has been hit by, let's say, some high energy particle, and then in that case it has grown from some ground state to a very excited state which goes beyond the 0-1 state. Then you have the leakage do the reset of the bits so that they can be brought to the 0 or 1 states. So that's where this combination that you see on the left-hand side is something which is very crucial and important. This is just representing the superconducting qubit lattice, and it's a logical qubit. For the others like quantum dot or neutral atoms, or even things like cat qubits, which are some of the latest, I would say, qubit fabrication techniques, we don't have representation done here on the board. So specifically, if we talk about this lattice itself, on the top you see D3, D5, and D7. So D3 is like number of data qubits. We have 3. D is nothing but the code distance. We call it as the code distance. This is nothing but this is number of qubits which are required to form a lattice so that we can have the error detection and correction done for some lower set of qubits. So if we have D equal to 3, then the number of errors that we can detect are D minus 1, which means 2 errors can be detected by this D cross D matrix, which is like 3 cross 3 system of qubits. And then out of these 2 errors that we have detected, 1 can be corrected. So the formula goes like, if you have D as the number of physical qubits, the space that you will be occupying will be D square, which is D times T. The number of errors that you will be able to detect will be D minus 1. And the number of the errors that you will be able to correct will be D minus 1 by 2. Okay? So in 3 qubits, you will be able to have 1 error corrected. In 5, if D equal to 5, then you will be having 2 errors corrected, and likewise in 7, you will be having 3. So that's the basis of how a superconducting based qubit system works like. So it's not the real physical qubit that you are working with. It's basically a bunch of qubits working together and set to have error correction done. That's why we have a branch called quantum error correction, or QEC. Because as I mentioned, errors are inevitable. You cannot really avoid them totally. You just have to go ahead, detect them, and correct them. Now we'll be moving to the second thing, more advanced topics before we get to our demos. And these are actually going to lay down some of the foundational aspects. What we need to understand is that quantum superposition, which my colleague Samrat explained, is very different from quantum parallelism. People actually have got a lot of misconceptions that parallelism is something that they can introduce by just using superposition. It's not like that. Parallelism is specifically a choreographed superposition and a sequence of the operations that you're performing on your quantum system. And it's a multi-qubit system. It's not just one qubit system, because in one qubit system, you have superposition. If you measure it, then it will fall to 0 or 1. But if it's going to be a sequence of qubits and all of them are in superposition state, then actually you can go ahead and try with some rotation of angles around the XYZ axis that we saw in the Q sphere. You can go ahead and make some phase-related changes. And at the same time, you can try to have parallel operations computed from the same quantum system. So it's a multi-qubit assembly that leads to quantum parallelism, and it's not that easy to achieve the same. So superposition is not parallelism. However, choreographed superposition could lead to parallelism. The other concept that we need to understand is the bit flipping and the phase flipping concept. So bit flipping is something, as I mentioned, it probably could be flipping your bit from 0 to 1, and it's something that noise could contribute to. Likewise, phase flipping is something that can also be triggered by the noise. So assume you have a superconducting ecosystem, you have a superconducting qubit created. On it, let's say there is some electromagnetic wave or some sort of photon interaction that has happened. Now at the substrate layer, there could be some energy which could be getting released, and the energy could be flowing in form of waves that we call as phonons. Now these phonons will be going ahead and could be exciting the system to change its state from the original quantum state to either something else, or if at all the energy level is something too much, then it can actually lead to something called as decoherence, which Samrat explained, which is the quantum properties of the system will be lost, and the system will be coming out of what it was intended to do, and hence it will also lose its memory because it's no longer computing on the same problem. It has actually got the higher energy level, and it has got excited. So we will need to, in that case, reset the qubit. So these are some of the core examples of the topics that you should be delving in before you really start working with quantum computers and quantum bits. And one more thing is people these days have got a bit smart. They have tried to see whether they can do a trade-off between bit flips and phase flips. So there is a company, Alice and Bob, which is trying to create something called as CAT qubits. These are electromagnetic qubits which work with additional photons to overcome the bit flip related challenge. So they minimize the bit flips that are happening in the system to a level that they just need to correct the phase flips. Now that means that they are going with more phase flips in favor of less bit flips, and that's where phase flips are more in number as well. So that's something these people are dealing with. But again, like every company and every research group that is in the quantum space is trying to go ahead and try to see how errors can be corrected in the most suitable format and in the easiest format. So then we get to the last point, which is how exactly we have this system of logical qubits acted upon on the actual quantum computer, on the actual hardware, or as we call as the quantum hardware backend. So the circuit that you bring up is actually compiled, or in quantum computing we say transpiled. So we will say the actual phase realization steps. So these are the phase realization steps. First you have the quantum algorithms created. You have the quantum bits arranged in a specific fashion. We will see one of the arrangements in one of the demos that we have. And then this arrangement of quantum bits actually could be independent of the hardware provider, because it's an abstraction that is being provided to you by libraries. So you could be having different libraries providing different abstractions to you, but in general, people follow some norms and they go ahead with having quantum circuits created in similar fashion for different SDKs as well that are available. So now you have algorithms or composition of gates, or you can have even kind of gates which are already big circuits realized as some of the smaller portions in even larger circuits. So it's like a combination of multiple circuits acting together. So ultimately you have algorithms and circuits. These get first transpiled. Transpilation is very much like you change it to assembly language sort of, and then you detect where you will be having the mapping done to the actual hardware backend. There is analog signal which goes, and ultimately you can imagine that there are some literal electromagnetic or microwave related signals that are sent, which are like pulses. These pulses actually help with doing the main interaction with the hardware backend, so that they can understand what kind of excitement needs to be given to a particular system, what kind of modifications need to be done with respect to bits and the phases, etc. So it's a pulse that actually travels from the time your stuff has got transpiled, and then actually it lands on the hardware backend where the real work is done or the processing is done. So it's not the qubit that you are programming essentially landing up. That qubit could be decomposed into multiple other qubits behind the scenes, And you don't know that just because that's an abstraction. Very much like if you write in assembly language and if you write in Python, things will be very different for you, right? So at the lower level, things are very different. So it's a high-level phase realization thing that we wanted to kind of showcase. So now let's go ahead and understand what we are trying to do. As part of this particular demo, we will be having a very simple problem from chemistry taken that's visualizing the molecular orbits for hydrogen. And we will be calculating some of the energy states. So the goal for us is to have the expectation value for any of the energy state related to this particular setup calculated. We first will be going with some classical computation. So there are libraries like PySCF, which are available, which can have approximation using an approximator called Hartree-Fock HF approximation. So we will be getting the ground state related energy from HF. And then we will be going ahead and trying to run these on actual quantum circuits. Today for our demo, as we need to enable you, the focus is to see how the cloud native audience can actually go ahead and try out the things at their own side. So that's where this particular code base is present. You can actually go ahead and scan this QR code. We have Python files. We have used Qiskit from IBM, which is an open source quantum simulator that is available. And likewise, we have Cirq available from Google as well, and there are some other companies also which have SDKs. For ease of reference for everyone, and because there are ample samples available for Qiskit online, we have gone ahead with Qiskit so that it's easy for everyone to follow. So in this particular demo, we will have this classical foundations first covered. Now, we will go through the code base once to help understand what exactly is happening. So is this readable at the back? OK. So what we have done is we have arranged the code, and as this is a demo, this is not production ready, so please don't treat it like that. There will be a specific arrangement of files. We have chemistry.py. This is actually having a bunch of functions for doing classical computing and HF approximation. And at the end, when we run our stuff on the simulators that are there on Kubernetes, we will be calculating the difference between HF and our calculated energy. So PySCF is essentially doing nothing, but it's calculating, as I mentioned, the traditional one. So what we do is we first have the atomic configuration specified here. This is initialization that you need to do. This is for the diatomic molecule. We are setting up how a molecule will be set up. And PySCF has some specific syntax, so it takes these digits per se to understand what kind of configuration there needs to be. And ultimately, it is just giving some base configuration so that it can have an origin point to start working with. We are instantiating this PySCF, and we are specifying that what the basis should be for our calculation, what kind of distance we need to have between the two atomic particles, and so on. And then there is a function here which is for running the PySCF calculation. This particular function is leveraging its driver, and it's going ahead and calculating the molecular energies. And it's just treating them as outputs which will be given back to the main caller for this particular function. We have a config.py. This is nothing but some fancy, I would say, data validation and config intake library sort of that we have implemented. This is for taking the configurations from a YAML file, because we are going to do the simulation first in local on our computer, then followed by running it in Kubernetes. So you should know how to have configuration externalization done. We'll be loading it as part of a config map that will actually be specified in YAML. So this is where all those YAML related input configuration methods are written. And then we have visualization as well. So we are producing an HTML file, as well as you can feel free to go ahead and choose a markdown or whatever you think is relevant for your use case. Then we have some optimizer settings. These are like what the tolerance level should be for the optimizer which is working. So when we actually run the simulation in Kubernetes, we will be running some optimizers. Those optimizers will be part of the VQE class. So that's a variational quantum eigensolvers. They are generally meant for having the expectation values for such kind of chemistry-related objects or problems calculated. And we will be using ANSAT's UCCSD. That is something but a type of, I would say, algorithm that needs to be followed again for calculating the chemistry-related problems. You don't really need to know about these things. These are just like some library-related calls that we are making. So this is how many number of iterations you should be running so that you can find the local minima or the convergence point. So ultimately, quantum systems, as I mentioned, that they are very much prone to errors. If you take one quantum reading, that could be highly influenced, or I would say skewed, because of the errors that it would have undergone, because it's really hard to detect the errors in one go. You cannot be certain whether your answer is the right one or not. So you actually need to run multiple iterations of your same problem and run it against the optimizers and simulators, and then go ahead and try to see where the probability is fitting for them. And let's say you have 1,000 iterations that you are running. In those 1,000 iterations, 800 say that you have a particular value which you should be treating as your output, then you treat that as an output, considering that you have applied the error correction code, etc., within your circuit. So tolerance, ROBEG, EPS, max iterations, these are just related to optimizers. There are different VQE optimizers, so we have optional configuration for all of them specified. This particular optional configuration also has some fallback optimizers, so Cobila, SLSQP, then SPSA, LBF, GS. These are all optimizers. Again, you don't really need to worry about. So what we'll be doing is we are actually calling all of these as part of the molecular configuration. So atomic label, we are having H2 as hydrogen. We are specifying the atomic distance, the bond distance between the two in angstroms. And then we are specifying how the visualization should look like, where the output directory should be, etc. We are specifying the molecular, the optimizers that we'll be using for calculating the molecular orbital related stuff, and then the optimizer related configurations. These are actually going to be fed locally, and then when we run in Kubernetes, they are going to be fed to Kubernetes. And visualization.py and main.py, these are just driver functions. We are just taking these calculations, doing some approximation for HF or the Hartree fork, and then comparing and drawing a chart as to how the ground state calculated by classical versus quantum looks like. So we'll go ahead and run this as part of our local. So I am currently just going to do a Python main.py. That's all what we need to do for this particular demonstration. We already have our libraries in our source for the Python virtual environment. And this will go ahead, load the environments, and ultimately start calculating the classical value, which is the HF value. And then it will start going ahead and using CPU because it's my local laptop. So now it has started doing the calculations. It will not take much time because I've kept the problem statement iteration very minimal, like 2,000 and 1,000. And you can see that the convergence is happening much before those. We will ultimately see a graph getting generated or a table getting generated comparing the different things. So let's give a minute and see how it turns up. Yeah. And in the meanwhile, I have just taken whole of this code base. I have templatized that into a Helm chart. So it's a job that is going to run because we don't really need to run it in a continuous manner. We just need to run it once for calculating or on demand. So it's a Kubernetes job that we are creating for running it in Kubernetes. And we are having those templates specified here. So config map, which has exactly the same molecular orbital configuration from config.yaml that we saw. I'm just going to collapse this so that you are able to visualize this better. And I'm going to have the size reduced a bit. So here you are having the optimizer show in terms of result. The Hartree fork energy that is there, it's -1.11, which is the approximate from the classical. Kobila is giving you minus 1.15 and so on. Ultimately, the rank has been calculated. I'm using pandas and pandas data frame in the background to have the calculation done for the rank. So Kobila has performed better. These 4 optimizers that you see have been actually run on CPU. And these are quantum-based simulations that I have run using Qiskit Air is the simulator that I have used. So you see that these are running on CPU. Now I have actually, just in interest of time, gone ahead and recorded for the Kubernetes one. We actually deploy this Kubernetes using Helm chart that we have. So it's a simple Helm upgrade -install Helm chart with the values file. We go ahead and see that the whole thing actually is working out of GPU. So now you see CUDA available equal to true. So that's where we have enabled NVIDIA system on which we are running the simulation. Then we are having GPU, and you see the shots, etc. also defined. So it's actually a simulation that is running on Kubernetes instead of our local system. And ultimately, you see that you have similar kind of things, but the time has shrinked. So on local computer, it was taking more time. On Kubernetes, it is taking less time because it is configured with GPU. Now, there are some key takeaways that we need to have from this particular demonstration. The takeaways are that quantum computing is expensive, so you really cannot go ahead and have the actual quantum computer or the hardware backend leveraged to run even your small set of experiments. That's where simulators really come handy, and running them on your laptop could again be time consuming, may not really fit your scale because you could be running quantum machine learning, you could be running some sort of advanced mathematical calculations which could be requiring GPUs. So that's where you might need a mix of CPU, GPU, and hence having a GPU environment, let's say enabled by Kubernetes or any other serverless platform, could really give you mileage. And then you can have some other advanced Kubernetes and CNCF or cloud native patterns leveraged, like the 4 optimizers that we saw, they were getting run in Kubernetes also in sequential manner. But what we can do is we can leverage a project named Ray. That Ray project can actually go ahead and have distributed processing done for these optimizers, so that we have now these 4 optimizers run in parallel on different GPUs as different pods. So instead of them running in the same pod as sequential processing algorithms, we can actually have the optimizers run separately using Ray, and we can have Ray workers which are going to have all these optimizers run in parallel. Likewise, if you are more in high performance computing, if you are more in, let's say, batch jobs or queue jobs, you can have Slurm leveraged along with Kubernetes or without Kubernetes to have the batch processing done, or you can have the queuing also done. Slurm can act like a scheduler for you. And if you want to go ahead with native Kubernetes-based scheduling, there is a project called Kueue, which is available, Kueue with K in the start, not Q. That is something which can give you a configuration through which you can have multi-tenant let's say, Kubernetes quantum simulations performed. So this is where, let's say, you have 10 team members from your research group who want to try out the Kubernetes-based quantum simulation at the same time for different problem statements. Now, they all will be running for and chasing the same set of resources. How do you have a fair share of resources among those 10 tenants or members of your team? This is where you can have a queuing algorithm, you can have priority classes, etc. And also, I know I'm just out of time. We have another talk which is happening, which is on declarative device virtualization in G107, just in 10 minutes. We explain another topic, HAMI, and how the MIG pattern for NVIDIA or MPS pattern, etc. work, how you can have declarative device virtualization for sharing the same GPU or the set of resources. Again, we have some demos as well to show to you. So with this, we have this particular talk concluded. Thanks a lot for being patient listeners and staying with us. These are our coordinates if you want to reach out to us. And once again, really, kudos to you for staying here, and thanks a lot. If anyone has any questions, we will be here for the rest of the day as well. We are just in G107 going for our other talk. After that, we are available at the center. Yeah, thanks.